Okay, so before we begin, I'll just give you a brief background on convex optimization that we will use here in this lecture. Okay, and subsequently you'll learn a lot about convex optimization in section B of this course anyways. So this is therefore something that's of benefit, immediate benefit to you. Okay, so Uh, just as a reminder, you're able to see the screen, right? Slides? Hello?
Yes, I am.
Okay. So
Yes.
the derivative of a constant is zero. Derivative of a linear term, derivative of P transpose X, which is the same as derivative of X transpose P. You can only take the gradient of a scalar function. Remember? So this is equal to P. And if you have a quadratic term, then the derivative of X transpose QX, which is Q is practically always assumed to be uh, excuse me, symmetric. This is the reason I thought Zoom would be better, because I have a cough. I don't want to infect you guys. But we won't assume that it is symmetric. So the derivative of this is Q plus Q transpose X. Now, when X is symmetric, the derivative, the first derivative is twice of QX. And likewise, the second derivative is simply twice of Q. Okay, and we'll use this here. So now this is what unconstrained minimum looks like. So you want to minimize a function. It's an unconstrained function in multiple variables. It's called a multivariate function. Still a scalar function because phi of x is scalar. So it's a scalar multivariate function. X star equals, we want to minimize this, right? So X star, star is indicates the optimum. So X star equals argmin of phi of X, right? And what must be satisfied is the first derivative must be equal to zero, right? Even just think scalars. The derivative has to be equal to zero at the minimum. And the second derivative in scalars, if x were a scalar too, univariate function, then the second derivative must be greater than zero, right? These are the first order and second order conditions for the minimum. Okay, and for vectors, it's the same thing. Instead of first derivative and second derivative, we use the gradient and the Hessian matrices. The gradient has to be equal to zero. The gradient vector now has to be equal to zero, and the Hessian matrix has to be positive definite. Okay, now when we have a constraint, equality constraint, we are only going to deal with equality constraints here. So here, again, we have to minimize a function, but now we have a constraint, a condition, AX must be equal to B. Okay. So X star equals argmin of phi of X with respect to X such that AX equals B. Okay, so this is constrained minimum X star. Now, what we do is, this is how we deal with constraints. In our trivial case, we have an equality constraint. So what we do is, instead of just taking the derivatives of the function itself, we construct something called the Lagrange function, or simply the Lagrangian. Okay, which is equal to the function that we want to minimize plus mu transpose times ax minus b. This I could have written as ax minus b equals zero. Something equals zero. That's an equality constraint. Okay, ax minus b equals zero. So this is the additional term in the Lagrangian. And mu transpose is equal to what's the dimension of mu? As many constraints as we have. If we had two scalar constraints, okay, then mu would be a 2 by 1 vector. If we had three scalar constraints, this is the vector constraint, remember? By scalar constraints, I mean the number of rows of A, which is the same thing as number of rows of B. If we had three scalar constraints, then mu would be a 3 by 1 vector. Okay? So this is the Lagrangian. And similar to these conditions, this is the first order necessary condition for the minimum. And this is the second order sufficient condition for the minimum. Okay, so what we have to do is now we apply something very similar to this. Okay, but instead of just the objective function phi of x, now we have the Lagrangian. So the first derivative, the gradient of the Lagrangian with respect to x must be equal to 0. And the second derivative of the Lagrangian must be positive definite. Okay? Now, this is with respect to x. Del x and del square x, okay, not mu. Okay, here's an example. This is what we want to do. We want to minimize this function. X is 2 by 1, so this is a bivariate scalar function. Okay, f of x, which is equal to, so we have a quadratic term and a linear term here. Subject to g of x equals this. Okay, now, since we can just look at it in simpler terms, if we just write it in terms of the scalars. So this is the same function. We have x1 and x2 as the two variables, correct? So this becomes equal to, let me, you guys could check if my math is correct. I just did it like 10 minutes ago. Okay, just made up this example. So we want to minimize this function. This is the scalar function, the scalar version of the same function, f of x, subject to now x1 minus twice x2 equals 0. We just have one scalar constraint. Okay? Now, what does this mean? It means that x1 is simply twice of x2, right? So we can replace x2 with half x1, and we'll just get one variable here, x1, if we replace x2 with half of x1. And then we can easily solve it using our knowledge of high school calculus. But let me stick to how you would deal in general with these constraint optimization problems. Okay, you will run into something more complex than this. Okay, okay. So this is our Lagrangian. Since we have just one scalar function, mu is a scalar. Mu is called the dual variable or the Lagrangian multiplier. Okay, both terms are equivalent. So this is the Lagrangian. Or in terms of scalars, it's this function here, f x1, x2, plus mu of x1 minus twice x2. And we simplify to this. And from this, you can differentiate with respect to x1. You'll get 4x1, this becomes 0, plus mu minus 4. So 4x1 plus mu minus 4, that's the derivative with respect to x1. And likewise, the derivative with respect to x2 is this. So this is the gradient of the Lagrangian or Lagrange function. Okay, and this is the Hessian. Hessian, I didn't have to differentiate, take the derivatives of this and this. I just used my prior knowledge that this is a quadratic function, and the second derivative of this is twice of q. This is q here. And q is symmetric, you can see. So twice of q is this. Okay, are you guys with me?
Yes.
Just checking. Is this a different version of the slides than is on Canvas right now?
Yes. I just
Okay.
wrote this like 30 minutes ago.
I was following along for the first like three slides, and
Ah,
all of a
okay.
sudden it was completely
Okay.
different.
Sorry about that. Yeah, I'll actually, right after this ends, I'll upload uh, this new version.
Awesome.
Okay. Okay. At the constrained optimum, this is what we should have. I need to get rid of this. I'll put it here. Okay. At the constrained optimum, so the gradient has to be 0, right? So this is the constrained optimum, x1 star, x2 star, and mu star. We have two primal variables. I call these primal variables, and mu the dual variable. Okay, so we have three variables in all. So I get two equations to satisfy here. And then uh, I also must satisfy this. It's a constrained optimum. So the constraint must be satisfied at the optimum, whence I must have x1 star negative 2x star equals 0. Correct? These are called the first order KKT conditions. The gradient has to be 0 at the constraint optimum, and the constraint must be satisfied too. Okay, there are other KKT conditions, first order KKT conditions, which you will look at when we have inequality constraints. Okay, so in altogether, there will be a set of four first order conditions that must be satisfied, KKT conditions. And the second order KKT condition is that the gradient of, excuse me, the Hessian must be positive definite. And the Hessian is clearly positive definite. So we won't bother about the second order KKT condition. It's trivially satisfied. Okay, so now we have three variables, x1, x2, and mu, x1 star, x2 star, and mu star. And these must be satisfied. We have three linear equations here, whence if we write it in vector matrix form, this is what we get. Forgive me if you find typos anywhere. Okay, I just made it up. So this, and if you solve it, you'll get the solution. X1 star, X2 star, and mu star. Mu star, you in this particular case, you don't have any need for mu star. So you'll get your solution x1 star and x2 star. That would be the constrained minimum of this object of this constrained optimization problem. Okay? So this is how you would solve a constraint optimization problem with only linear equality constraints. Am I clear? Everyone good?
Yes. Yes, I
Okay.
believe so.
So now let's begin with the topic of today's lecture, and this you will find in the slides. So matrix pseudo-inverse and linear systems. Okay. So these are the topics, and what you those of you who've done 540 would find novel is, well, may or may not be the polynomial fitting application, but certainly the probabilistic explanation would be something that's new to you. Okay, so what we have here is how do I get rid of this? This is a big Okay, this is a big bother in general whenever I do Zoom lectures. So we have m equations in n variables. Okay, and m and n need not be of the same size. Okay, and we have to solve ax equals b, where A is a m by n matrix. Missouri and Nebraska, I'll just use our neighboring states. So Missouri and Nebraska, and X is a n as a Nebraska dimensional vector, and B is a m dimensional vector, m as in Missouri. So this, in general, is the solution. X equals A pseudo inverse B. The pseudo inverse of this matrix A plays the same role as the inverse of a symmetric uh, full rank matrix. So the pseudo inverse is a generalization of the concept of a matrix inverse. Okay, but not all uh, properties of the inverse would be satisfied because these are not square matrices. Okay, now we have two situations. First case is when m is greater than n. So this is a m by n matrix, correct? So when m is greater than n, it looks like a tall matrix. So um, maybe m is 100 and n is 10. So 100 by 10 matrix. So it's tall. Okay. In which case, x equals a plus b is an approximate solution that minimizes the square norm of error. We'll see how. Okay, why is it an approximate solution? Because we have to satisfy, let's say m is 100 and n is 10. M is greater than n. So we have 100 linear equations and only 10 variables. X is 10, size 10 vector, right? So we cannot expect to satisfy 100 linear equations with 10 variables. So we look at an approximate solution. Okay, and a pseudo inverse is given by this expression, and you will see, you can immediately see why, but A transpose A is invertible. I'll show you graphically. And rank of A is n. Rank of A cannot exceed the lower of the two dimensions. If it's 100 by 10 matrix, then rank of A cannot be more than 10. Okay, although we have 100 rows in A. Okay, now the second situation is where m is less than n. So the number of rows is less than the number of columns in A. Maybe m is 10 and n is 100. So we have 100 variables, but we have only 10 linear equations to satisfy, linear equalities. Okay, so we can have multiple solutions, infinite number of solutions, right? So in this case, A is called a wide matrix because the number of columns is more than the number of rows. We'll call such matrices wide matrices. And the rank we'll assume to be the lower of the two, which is again m. Again, the solution is x equals A pseudo inverse B, but this time it's the exact solution with minimum squared norm. I'll explain what this means. Okay, so in this case, the pseudo inverse is given by another expression here. This is the expression for the pseudo inverse for a wide matrix A. A transpose, A inverse, sorry, A transpose inverse. And the rank of A has to be the minimum of the two. Okay, and A transpose will be invertible. If m is 10 and n is 100, then A transpose will give you a 10 by 10 matrix, and that will be invertible. Okay? So overdetermined systems is the first situation. So we have m equations in n variables. M is greater than n. Okay, so we have m equations. M as in misery, and we have how many variables? X1 through xn, so n number of variables. So less number of variables, more number of equations to satisfy. The ith row in general would be this. AI1 x1 plus AI2 x2 plus dot 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 until AIn xn equals BI. Or summation Aij xj equals BI. This is the ith row. We have more equations than the number of variables. We have 10 variables if m is, sorry, if n is 10 and m is 100. So we don't have an exact solution. We'll try an approximate solution. Okay, so we can express this equality, what we want to solve in this form. Note that I have replaced the equal sign with this because we are looking at the approximate solution. We cannot expect to get the exact solution. Okay, so visually, this is what it looks like. And A is a tall matrix. This is the ith row. So what we have to do is, since we cannot exactly satisfy this, so what we have is summation j ai jxj must be approximately equal to bi. Okay. So this is what for each row I, we must satisfy this. For the same ith row, let's define the error to be the difference. Bi minus summation aij. Okay. The error might be positive or negative, correct? But we want the absolute value of the error to be as small as possible. Or alternately, we want the square of Ri, the error, to be as small as possible. Okay. So in terms of vectors, the vector of errors is R1 through Rm. And by the way, throughout this course, this will be a shorthand notation for a vector R1 through Rm. Ri, where I is from 1 through m. Okay. And since Ri is equal to this, we have R equals B minus AX. Okay. So R is the vector of all errors. Each scalar expression has its own error, Ri, and we concatenate them to get the vector of errors. And each of these components of R could be positive or negative, correct? So what we want to do is squared norm error or some squared error. Okay, this is phi of x. We want to minimize this summation of Ri squared. Or vectorially, this is the squared error R transpose R. Are you guys with me?
Yeah. Sorry, I have a
This is,
question.
yes.
Okay, and when we have more equations than the number of our variables, so why we can't, find the exact value of the variable? I mean, I don't understand that. When we have enough
Well,
equations.
how about x and y? So how about solve 2x plus 3y equals 5, 4x minus y equals 7. We have x and okay, so x and y, and let's have three equations. Solve 4x plus y equals 7, 3x minus y equals 4, and 8x plus 2y equals 3.
Okay.
Right? So we have three equations. Can we solve all three of them?
No,
No. In fact, unless one of them is linearly dependent, if the A in the matrix A, one of the rows, we have a 3 by 2 matrix A this time. One of the rows would be linearly dependent. Okay, in which case the rank of the matrix, although we would have a 3 by 2 matrix in this example, sorry, I don't have slides for that, the rank would be 2, right?
Yeah, thank you.
Okay, so, well, the rank of this matrix is anyway 2. So how about this? 3x, let's take a single variable and satisfy 3x equals 1 and 2x equals 4. Can you find a solution x?
No.
Right, it's the same situation.
Yes.
Okay, so we want to, this is the error vector, also called the residual. That's another term. Okay, this is the residual vector. We want to minimize R transpose R, which is the same thing as the squared L2 norm. Correct? So R is this. This is what we want to satisfy. This is, excuse me, what we want to minimize. Okay, R transpose R. This is our objective function to minimize, which is, since R is V minus AX, we have this, the expression for R transpose R, phi of X. And let's open up the parenthesis. So B transpose B negative AX transpose would give you X transpose A transpose. So X transpose B, and then B transpose AX, B transpose X. Don't ignore the negatives, so we have negatives here. And then the last term would be AX transpose times AX, which is X transpose AX. Okay. So now you know that this is a scalar function, right? R transpose R is a scalar. Each term has to be a scalar, right? For a scalar, the transpose of a scalar is equal to the scalar itself. Okay, so B transpose AX, if we take the transpose of this, S must be equal to B transpose AX. So let's replace this scalar with its transpose. Okay, the transpose of B transpose AX is X transpose A transpose B. So we replace this with X transpose A transpose B. So we have these two terms are identical. Hence, I get, this is the first term, the second and third term reduced to this negative twice X transpose A transpose B, and then this is the final term, X transpose AX. Okay? So the first derivative is, this is overdetermined systems. So we have to minimize this, right? And we don't have any constraints. We're just finding x so that this is minimized. So the first derivative is this. What's a differentiate B transpose B with respect to x? 0. Differentiate this, negative 2 x transpose times a vector p in general. So it'll give you p. So negative twice A transpose B. And then the derivative of this is, you can easily check that this is A transpose A is symmetric. Okay, so it gives you plus A transpose AX, twice A transpose AX. This is the first derivative. If you just apply the expression in the very first slide today. And then the second derivative of the sum squared error is this. Second derivative of this is, well, just drop the constant term, the linear term. This is the quadratic term. So X transpose QX, where Q is symmetric, so it'll give you twice of Q, right? So in our case, the Hessian is twice A transpose A. And we've seen that A transpose A will always be positive definite, as long as we assume that A is full rank, by the way. Okay. So at the solution, X star, we must have, this must be equal to 0. The first derivative, the gradient, must be equal to 0. Correct? Whence A transpose A X star equals A transpose B. I just dropped the 2 on both from here. Okay. Whence X star equals A transpose A whole inverse, just solve this, times A transpose B. Are we guys good?
Yes.
Yes.
Okay. Now we have n equations in n variables. Look at this. We want to solve this. This is our original purpose. We want x such that ax equals b. What we did is, now, for reasons we just saw, this is an approximation. Okay, so we have m equations in n variables, more equations than variables. Okay, now what I'm doing here is ax equals b. I pre-multiply both sides with A transpose and replace this approximation with an exact equality. So A transpose AX is A transpose B. Now, A transpose A is a square matrix, right? This is an M by M matrix, A transpose A, and this is a M by 1 vector. Excuse me, this is A transpose, so sorry, I misspoke. It's an N by N matrix. A transpose A is N by N, Nebraska times Nebraska. N by N, and this is a N dimensional vector. So we have N variables and N linear equations, right? And we can easily solve this. Same number of variables as the number of equations. And this is our solution. So this is what we are in fact doing. We want to solve this where m is greater than n. And so this is how we formulate our problem. We want to minimize the sum square error, which is the same thing as the R transpose R, where R is the vector of errors. So we want to, this is our solution. X star equals this. How do we solve it? We get this. We get these expressions. Ax equals b. We just pre-multiply both sides with A transpose, and so we get an n variables and n equations, and same number of variables as equations, and we can solve this. Okay, the solution X star is given by this expression here. A pseudo inverse B, and when A is a tall matrix, here you can see visually A is a tall matrix, so A pseudo inverse is given by this expression here. A transpose A is this matrix here, which is n by n. Okay, and it's invertible. And so A plus is the pseudo inverse, and A pseudo inverse times A is this, and which is equal to the identity matrix. A transpose A inverse times A transpose A is the identity matrix, right? But A transpose will never be equal to the identity matrix. Why not? Because A transpose will be a M by M matrix, M by M, misery times misery, right? A transpose. So it'll be, if M is 100 and N is 10, this would be 100 by 100 matrix. But what's the rank of A? 10, right? So it's, if you take, this is A pseudo inverse is 100 by 100 matrix. but A is of rank 10, right? So you can never get the identity matrix, because the identity matrix would have a rank of 100, but you cannot get, if you take matrix of rank 10, no matter what you do, pre-multiply, post-multiply, you can never exceed 10. Okay, so these are the properties of the pseudo-inverse for a tall matrix. Okay, so this is an overdetermined system, and this is the solution. Okay, now how to solve this? Well, numerically, of course, A transpose A is positive definite, so we can use Cholesky decomposition and then solve it like this. Okay, or we can, if whatever software package you use, which is in our case MATLAB, if it has a subroutine, built-in subroutine, which MATLAB does for pseudo-inverse, then x equals A pseudo-inverse B. Method 3 is QR decomposition, and that we will see in the next lecture. Okay, now here's an example. Now this example make it clear. We have two variables, x1 and x2, and we have to satisfy three linear equations. We cannot expect to satisfy all three, right? We can only try to approximately make the right side and left side as close to one another as possible. So what we do is we just pre-multiply both sides with A transpose, and then we get this. So this is really nice. We have same number of variables as the number of equalities we want to satisfy, and so we go ahead and solve this. And this is our solution. This is the solution, x1, x2. Note that if you plug in the variables, it won't satisfy all three of these linear equations. But the errors will be small. The differences between the left-hand side and right-hand side would be small. Am I clear? And does this answer your question properly? Who asked this question? I forgot.
I have one question.
Absolutely.
Is there any way that we can decide, or is there any times when Cholesky would be better than the pseudo-inverse and vice versa?
Well,
Or is it
first of
just
all, pseudo-inverse is a built-in command in MATLAB too. Okay. So, and it has its own algorithm, which I assume would be even better than doing Cholesky decomposition. Okay.
okay?
But suppose
Got
you
it.
didn't have, then since you know that A transpose A is positive definite, we can use Cholesky decomposition.
Okay, got it.
Okay.
Thank you.
Here's an example of where this overdetermined systems is useful. Okay. Suppose maybe we are cops on a freeway and we are tracking the speed of a truck. We want to estimate if what's the velocity acceleration of this truck. Okay. So you know that the displacement is the initial displacement plus initial velocity times t's at time instant t, so times t plus half acceleration times t square. X equals x naught plus v naught t plus half at square. We all know this. Okay. So this is the expression. Now we take So in general, this is what we have. These are unknowns. We can record the time. Okay, so these are the unknowns. Y naught, V naught, initial velocity, initial displacement, and the acceleration. So I'll call them alpha naught, alpha 1, and alpha 2. So this is an expression we have. Y equals A naught plus A1t plus A2t squared. Okay, so the unknowns are these, not t. Okay, I'll explain. So the unknowns are A naught, A1, and A2. And now suppose we take 100 samples. We record the time and the displacement. And so we get 100 samples. T1, X1. At time T1, the displacement of the truck was Y1. At time T2, the displacement was Y2. And at T100, the displacement was Y100. Okay, so these are known. Each Ti, Yi is known. T's and Y's are known. The unknowns are alphas. Okay, so we want to satisfy these. All 100 observations have to be satisfied, right? These are 100 samples. All 100 samples have to be satisfied with alpha naught, alpha 1, and alpha 2. Agreed? Do you see this?
Yeah.
Okay. And obviously, maybe due to experimental error, obviously, in this case, there would be experimental error. We cannot satisfy all of these 100 equations, right? In fact, we took 100 sample observations only because we know that there would be some instrumental error. Okay, so now we want to estimate alpha naught, alpha 1, and alpha 2. In general, so we have m samples like this. And we want to satisfy, we took constant acceleration, but in general, for some other situation, we need to satisfy y equals alpha naught plus alpha 1t plus alpha 2t squared alpha n minus 1 t to the n minus 1. Okay, so we have n minus 1th order polynomial. And the alphas, how many alphas do we have? Alpha naught to alpha n minus 1, so n number of unknowns. Okay, so we have large number of samples, in our case m, and we have n number of variables, alpha naught to alpha n minus 1. Okay, so we want a suitable polynomial approximation, so y approximately equal to this, which best fits all m experimental observations. These are the unknown coefficients. Okay, and we can, so y1 is equal to this from sample 1, from sample 2, and so on. So from the last sample, this. So we have to find the coefficients, alphas, alpha naught to alpha n minus 1. Okay. So this is what we have. And in terms of vector matrices, this is what it reduces to. Okay. Now this is a tall matrix. We have M. M in our example, previous example was 100, right? So we have 100 observations, large number of samples. And we have a relatively less number of unknown coefficients. So this is what we want to solve. Okay, we know there is experimental error, right? So there would be, this would be an approximate, approximately equal to, and we want to find the best values of the alphas. And so what we do is, so this reduces to V alpha equals Y. V is called the van der Mond matrix. Okay. This is very commonly used in lab experiments like this. So van der Mond matrix, this is the format of a van der Mond matrix. It need not be time, it can be something else too. Okay, and so alpha equals this, V pseudo inverse Y. This is the van der Mond matrix. Okay? So this gives you one of the possible situations where you would come across overdetermined systems. The next is underdetermined systems. Let me just quickly check the time. 52 p.m. Okay. So underdetermined systems is the opposite. Okay, so we have more variables and less number of equations. Again, this is the ith row. And since we have less equations than the number of variables, we have so many solutions. In fact, we have infinite number of solutions. Okay, so which solution do we actually seek? We have to set up some framework to get a single solution, right? Instead of all infinite number of solutions. So we want to fix an objective function to be minimized. Okay. So this is in vector matrix form. This is a wide matrix, and this is how it looks like graphically. And we'll assume that A is full rank. In full rank, by that I mean whichever is lower, M or N. In this case, M. So this is a matrix of rank M. M as in misery. Okay? So what we do is we want to, this is the objective function that we set up, and I'll give you a justification later. X, we can have infinite solutions, right? So we want to find the min norm solution. We want to minimize, we want to find a solution whose length is the minimum. Or in other words, we want to find a solution X such that X transpose X, or which is the same thing as L2 norm squared, should be minimized while satisfying Ax equals B. Okay, so this is what we want to get. X star, now instead of infinite solutions, we want to find which of those infinite solutions X, which would satisfy this, has the smallest length, or the smallest squared length, which is the same thing as the L2 norm squared. Okay, so this is our constrained optimization problem. This is what we want to minimize. For convenience, I just added half here, half of summation xj squared, subject to ax equals b. So for each row I, this must be satisfied. Summation aij minus bj should be equal to 0. Okay. How many constraints do I have? Equality constraints. For each row, how many rows? M, right? So for each scalar constraint, I must have a corresponding dual variable or a Lagrange multiplier mu I. And this is the Lagrange function or Lagrangian. This is a constrained optimization problem, and this is a Lagrangian. And mu is an m-dimensional vector. In terms of vectors and matrices, this is what I have. Minimize half x transpose x subject to ax equals b, or ax minus b equals 0. And so this is our Lagrangian. Objective function plus mu transpose times the constraint. Ax minus b equals 0. Okay? And so what we do now, we apply the KKT conditions which we saw earlier in this lecture, at the beginning of this lecture. So this is our Lagrangian. We want to apply the KKT conditions and find the solution X. Okay. So this is the Lagrangian. So the first derivative must be equal to 0, right? What's the first derivative of this Lagrangian function with respect to x? The gradient. Derivative of half x transpose x is x. And so take the derivative of this. Mu transpose ax would give you A transpose mu. And mu transpose b is constant with respect to x, so that's 0. The second derivative is basically this is half x transpose times the identity matrix times x. Ignore the linear and constant terms. What's the second derivative of the Lagrangian? It's this, I. Agreed? Are you guys with me?
Yeah.
So,
Yep.
this is the second derivative must be positive, definite, and that's trivially satisfied. You can see, since it's the identity matrix, second derivative is always satisfied. So we simply have to apply the first order conditions and ax equals b, and then arrive at the optimum. Okay, so the second one is all satisfied. So just ignore the second order conditions. Okay, so we'll look at these. R equals 0, or x star equals negative A transpose mu star. Okay, we just used up this expression here. And then we have Ax equals B. So now we have two equations. X transpose equals negative A transpose mu, and we have Ax star equals B. That's the constraint. Okay, so just let in Ax star equals B, since we have X star equals from this expression, we know that X star equals negative A transpose mu star. So replace X star with negative A transpose mu star. We get negative A times A transpose mu star equals B. Or mu star equals negative A transpose inverse B. So we found out mu star, but we need X star actually, right? So how do we get X star? We use this relationship. X star equals negative A transpose mu star. This is mu star. Okay, so using this, we get X star equals A transpose times A transpose inverse B. And what is this? A transpose inverse. That's the pseudo inverse, right? So X star equals a pseudo inverse B is our solution, where a pseudo inverse is given by this expression. And a pseudo inverse will be equal to I now. And for obvious reasons, a pseudo inverse times A won't be equal to I. It won't be full rank, a pseudo inverse A. Okay, so this is how we tackle an underdetermined system. And this is one of the approaches when we want to minimize the length of the solution, the squared L2 norm of the solution. That if we wanted to satisfy the L1 norm, then we would obviously use some other approach. Okay, or we could set up some other formulation too. Okay, but this is one approach. Are we good with this?
Yeah.
Yep.
Okay. Now, why minimize L2 norm squared? Okay, now here's why. Now, in general, okay, now in practical situations, maybe we are looking at only positive values of x, but let's say we are dealing with neural network weights, in which case there is no reason why an x is more likely to be positive. Okay, it can be it's equally likely to be negative and positive. Each of these variables, x's. Okay, so what happens is we assume that each scalar x follows a Gaussian distribution centered around 0, with 0 mean. Why do we choose Gaussian distributions? In general, is there's a philosophy behind it. Suppose we want to find a distribution with given mean and mu and covariance lambda. Okay. Only we are given the mean and the covariance. There could be so many distributions, right? Any number of distributions. The Gaussian distribution is the distribution of all those candidate distributions. The Gaussian distribution is the one that minimizes the amount of extra information that we use from an information theory standpoint. In other words, we want to minimize the entropy of our solution. Okay. It's called the minimum entropy principle. So we assume for these reasons, philosophical reasons, actually statistical reasons, let's assume that X follows a Gaussian distribution. And since the covariance matrix is not specified, we just assume that it's I. And the mean is 0 because there is no reason to expect that X would be more positive or more likely to be negative. So it's centered around 0. So this is our PDF of X. Okay, centered around the zeros, 0 mean. And we assume that the variances are 1. Okay, so this is the distribution, the Gaussian distribution in n dimensions, right? With covariance matrix, the identity matrix being the covariance matrix and mu being 0. This is the probability distribution function. Okay, the Gaussian distribution. This is the multivariate Gaussian distribution. Okay, and its log is this. Negative half x transpose x and minus, because it's a minus n by 2 times log of 2 pi. Okay. Now, we want to find x which is most likely. Correct? So we want to find ax equals b, we must satisfy, but we want to find which of those x's, which satisfies ax equals b, is most likely. In other words, we want to maximize this p of x subject to ax equals b. Okay, but you see this is more complicated. So if we take the logarithm, maximizing this p of x, instead of that, we can just maximize the log p of x because the log function is monotonically increasing. Okay, so instead of maximizing p of x, we choose to maximize the log P of x, which, by the way, is called the log likelihood. Okay, which is equal to, I replaced the expression for the log likelihood here. This is the expression. This is what we want to maximize. We can simply drop this, right? This is constant independent of x, the second term. So argmax of negative half x transpose x. Okay, it is this. But instead of maximizing the negative half x transpose x, I minimize. Okay, I drop the half. And so just another step. Instead of maximizing the negative, I choose to minimize x transpose x, subject to ax equals b. So this is the theoretical justification for the approach that I presented. Okay. This is a little deep, but since this is not a statistics course, but otherwise this would be fairly trivial in any statistics or machine learning course. But so this is our approach. We have ax equals b. We want to find x. This is how we set up our problem, and that is the log likelihood. We want to maximize the log likelihood of x. Okay. So any questions with this? Did you guys get the whole idea of what I'm trying to do here? This.
Yeah.
Okay. This is actually the maximum likelihood estimator. Estimator is the core topic in any machine learning course or deep network course. Okay. It's also called ridge regression. Have you heard of ridge regression?
Yes.
And
Heard of, but never done.
and you could have heard of lasso regression, LASSO. If
I'm not sure I've heard of that one.
LASSO, lasso regression and ridge regression, that's so common. Okay, and so if you instead of a Gaussian distribution assumption, presumption, if we assume that this x followed a Laplace distribution, here the quotient, this constant term would be different, of course. This would be a negative of L1 norm, not L2 norm squared. Okay, then the approach would be different. Then we would be trying to solve this argmin of L1 norm of x subject to ax equals b. That's lasso regression. But the way I did it is ridge regression. RIDGE. Okay, lasso regression, LASSO, it's an acronym, and ridge regression are so commonly used. Okay, you'll come across this everywhere in machine learning and in other areas of engineering too. Okay, so this is the gist of what we did. We have ax equals b, but the number of equations and the number of variables are not equal. This is the general solution. X equals a pseudo inverse b. When A is a tall matrix, then we simply try to minimize the square norm of the error. Okay, and so we get an approximate solution. X equals a pseudo inverse b. If you plug in this value of x that you get, you'll see that doesn't have to satisfy A equals B, AX equals B. Okay. Otherwise, when A is a wide matrix, then we can get an exact solution that minimizes the squared norm, a ridge regression. And again, this is the expression for the pseudo-inverse. Okay. So for those of you who've taken what was the undergraduate version of this? 570, right? Did you gain enough insights, further insights? I hope you did. First of all, this formulation as a constrained optimization problem, okay, and the reason why we use this X transpose X we want to minimize, the theoretical justification for that. Okay, so this will end today's lecture. What questions do you have overall? Come on, feel free to. We have about 7 more minutes. Feel free to ask any question. Even if it sounds dumb, there's no need to inhibit you because you're not expected to know anything. Nothing, no question is dumb. Of course, unless what do you mean by a matrix or whatever, that's different. Okay, go ahead, any question, please.
I have a question.
Sure.
So when we do not know the underlying distribution of the data we have, how do we choose whether to use L1 norm or L2 norm?
That depends on uh, so many practical considerations or a convenience too, whether to use L1 norm or L2 norm or something else. By the way, do you know what's the zero norm of a vector? L1 norm is the sum of the absolute values of the scalar terms, right?
Mhm.
But what is the zero norm of a
The
vector?
number of terms.
Number of non-zero terms. Okay, so in some cases we want to keep the number of non-zero terms to a minimum. So we want to minimize the L0 norm, zero norm. This is a L2 norm. Okay, so if we want to minimize the number of non-zero terms in X, if we expect for some reasons, reasons that have to do with the application, we want to keep the number of terms in X to be at a minimum. In other words, we want to make sure that a lot of the elements of the vector X are zeros. Okay, in which case we can use L0 norm. But L0 norm is not differentiable, it has problems. So instead of L0 norm, it's convenient to replace L0 norm with the L1 norm. Okay, you will still be getting a lot of zeros in X if you use L1 norm instead of L0 norm. That I might visit and when we do optimization, depends on how it flows. Okay, so what people use is in practical applications, they often use something called the elastic net. It's a combination of the L0 norm and L1 norm, the elastic net approach. Okay, so there's so many different approaches. It's a complete different topic altogether, but something that you might be, you should be aware of, and you might come across these issues in your graduate research. Okay. And remember, why do we, everywhere, we assume that, okay, X follows a Gaussian distribution. That's pretty standard. And we just blindly assume that it's a Gaussian distribution without understanding exactly why. Okay. That's because the Gaussian distribution is the equation which is the distribution, excuse me, which minimizes the or which maximizes the entropy when the mean and covariance matrices are fixed. So it's a maximum entropy solution. In other words, we are not throwing in some additional assumption. If we had chosen a Poisson distribution or any Cauchy distribution, any other distribution, then we would be implicitly making more hidden assumptions without knowing it. Okay, that's why we use the Gaussian distribution. It's so common. Does this make sense?
Yes.
Okay. Most of the time, you just make this assumption without knowing the underlying reason why. Okay, let's assume it's a Gaussian distribution. Okay, you'll come across that all the time in grad literature and research papers, textbooks, this assumption, but this is the reason why. Okay. So let's conclude. If you have any other questions, otherwise we'll conclude.
Thank you, Dr. Das.
Okay. Nathan, Rehane?
No questions right now, so I can catch you next week.
Okay.
Thank you.
Okay, and stay safe. Steve, it's pretty cold outside. Okay. So let's quit then.
Bye.
Bye.